Hi, I'm Will. I'm one of the co-chairs for the project side of Climate Match, and I'm also a postdoc at Princeton University, where I work primarily on trying to use machine learning to understand sea ice changes in both the Arctic and Antarctic. But today I'm going to be introducing the project, which will look into how sea ice has changed in the Arctic region specifically. So when we talk about sea ice, we're talking about this thin layer of ice that forms at the ocean surface when atmospheric temperatures get sufficiently cool enough to freeze the ocean surface. And it's a particularly important component of the climate system. You can see in this picture here on the left, sea ice forming at the ocean surface. And we can see how the high albedo nature of this sea ice surface means that it has a tendency to reflect incoming solar radiation. So the high albedo means that incoming solar radiation is reflected back into the atmosphere, into outer space, whereas the darker regions of the ocean surface have a tendency to absorb sea ice. So this has the effect of keeping the Earth's surface temperature cool. And sea ice is also important for various human and natural systems as well. There are some 4 million people who live in the Arctic region, and a significant number of which are indigenous communities who depend on the sea ice for things like travel. And there are also various endemic species in the Arctic who also rely on sea ice for things like hunting and habitat. So, just getting a first look at sea ice, then we can look at this video animation by NASA, which shows how the sea ice undergoes a dramatic change every year due to the seasonal cycle of solar insolation that happens in the Arctic region. So, as spring comes around in around April, May time, we start to get melting of the sea ice, and then we can see how this leads to a shrinking of the sea ice cover as the summer progresses. We can see here we start to lose ice in regions such as Baffin Bay here on the west of Greenland, and we start to open up these areas of open ocean around the Eurasian coast and also on North America. We can see this here summarized in this plot, which is showing the seasonal cycle of sea ice across the year. So, and for a different number of years spanning from 1980 to present. And what we can see here is that the Arctic reaches its maximum extent around March time and then reaches its minimum in September. We can see this is a dramatic change in cover. We go from roughly 16 million square kilometers of sea ice down to about 3 or 4 million square kilometers in summer. So this is a huge change and has massive implications for the Earth's climate. And just to put that into context, the kind of total surface area of the European continent is about 10 million square kilometers. So some of the data that you'll be working with as part of this project is related to sea ice concentration. So what is that? That's what we're going to summarize here in this slide. So sea ice concentration basically summarizes the amount or the area fraction of a given grid cell that contains sea ice. So we can see here if we have a map of sea ice concentration shown here, we can zoom into that and see that in each grid cell we have a value of concentration which corresponds to the fraction of that grid cell which contains sea ice. So here we can see a value of 0.75 means 75% of this grid cell contains sea ice. And a useful thing to be able to derive from these kind of data sets is this allows us to tell how much total sea ice cover there is on a given day, for example. So we can say that for a given grid box, if this has a size 25 kilometers by 25 kilometers, we usually define some threshold for how much sea ice there is in a given grid cell. Usually that's defined as 15%. So what we can do is we can define the total extent of sea ice on a given day or year as the sum of the effectively grid cell areas for which sea ice concentration is greater than 15%. So you can see here we would sum effectively 25 by 25 for all of these grid cells except for the ones here that are lower than 15%. And that would give us an estimate of how much sea ice there is in the Arctic. In this case, that might be something like 7 million square kilometers. And being able to compute things like sea ice extent has allowed us to track the change in sea ice cover that's happened over the last 40 plus years. And we can see that, particularly in summer, there's been a declining trend in sea ice, shown in this video animation here, where we can see
Wow.
since 1979, we've had a
This year's
downward trend in sea ice due to anthropogenic climate change. We can see in this summary statistic here that the amount of sea ice loss represents effectively roughly 40% of the total summer sea ice that's been lost in the last 40 years. And this has big consequences for the Earth's climate. Due to this sea ice loss, we've been exposing areas of open ocean more and given what we talked about earlier in terms of how the ocean has a propensity to absorb solar radiation, these areas of now consistently open ocean have led to further warming in the Arctic region. This is something referred to as polar or Arctic amplification, and this has caused the Arctic to warm at roughly 4 times as much as the global average. And this in turn has implications for some of those human and natural systems which we talked about already. So something we've also got to think about is what are the future impacts of climate change in the Arctic region and on sea ice in particular. And this is something you'll be looking at as part of the sea ice project using model data, so model simulations from a given CMIP6 model to look at how sea ice will evolve under different future greenhouse gas forcing scenarios. And the models also output variables like sea ice concentration, which allow us to compute metrics like sea ice extent for those models as well. So we'll be able to look at how sea ice has changed in that model over the historical period, which is usually given as 1950 to 2014 for CBIP6 models. And then for different forcing scenarios, so we'll be looking at one of the lower greenhouse emission scenarios, 126, seeing how sea ice changes along that trajectory, and also for a moderately larger increase in greenhouse gas forcing with 2.5. So based on that, we'll be able to see how the extent or the ice cover changes into the future and be able to assess based on different criteria when we think the Arctic might first become ice free.